Ladies and gentlemen, we are going to talk about something called conjugate addition. Conjugate addition. It happens right here. This one here is the conjugate addition product. And in this case, the conjugate addition is called a 1,4. And this is the normal addition product that we've seen before when the anions attack carbonyl. We're going to rename it though, 1,2 addition, as opposed to 1,4 addition. Right now, we don't have enough information to even describe what those words mean. 1,2 addition, 1,4 addition. Once again, I'm going to ask you the pKa of this species. And you're going to say 10. And why is it called diethylmalonate? That's a good question. That's a malonic ester. Really, it's a malonic diester. Malonic, oh my. Oxalic malonic. 2 carboxylic acids in a 3-carbon molecule. Got it. They become esters, so it's a malonic ester. pKa 10, we're going to take its H off. And this is going to become our nu. Older nu. Let's do something like that's an organolithium, right? Why is this one much more reactive? Than the new at the top of the page. Why is it much more reactive than the nucleophile at the top of the page? This one. There's a lot of resonance up here that stabilizes this one. This is very important. This thing has 0 resonance. This thing needs to make a bond and be done with being an anion. It hates being an anion. It hated it the moment it was formed. That's how reactive that thing is. Isn't it the strongest base you know? Which means it's a really strong nucleophile too. Okay? All right, this one, we call it if you use a strange lingo that organic chemists like, it's called a soft nucleophile. And things that resonate or are stabilized by large sizes are soft, as opposed to like say a fluoride ion, which is really tiny. It's an anion that's really, it's tight. That's not soft, that's hard. Okay? But you know, iodide out here, electrons are really soft and mushy. They can be moved around and, you know, pushed to one side of the iodine atom. You can't do that with a fluoride. It's stuck there, it's an anion, it's all right there. Hard, soft. I'm never gonna ask you about hard and soft stuff, okay? But when it's soft, it's stabler, more stable. And it can resonate, because that's why this thing's more stable. I need to show 2 separate mechanisms, ladies and gentlemen. Sadly, I forgot to draw this 2 times for you. It's the same anion twice because there's 2 products. And the same reactant here, reacting with it. So you need to draw that, both those things again. Now, in this bottom one, I'm going to show you the reaction you've learned before. Like if this was an organolithium, what would you do? You'd go straight for the carbonyl, right? And why do you do that? Because the carbonyl is quite positive and the oxygen is quite negative. That draws these electrons to the positive part. And we call the atom that gets attacked position number 1. And where the electrons flow next is 2. And if they flowed farther away, it would be 3, 4, et cetera, et cetera, et cetera. We're going to see 1, 4 later. But now you're seeing where the 1, 2 came from. I'll put it in pink now. It's a description of a mechanism. Those numbers are only talking about a mechanism. Nucleophile hits atom number 1, electrons flow up to atom number 2. That describes the actual mechanism I did, doesn't it? Let's draw the result because it's almost done for that last product. And in fact, let's use my space a little more judiciously. We have CO2ET, CO2ET, new bond here to an O minus, which is attached to C-double-C dimethyl. If you flip that over, you can definitely see that it's related to that product up there, isn't it? Just flip it. I lost a methyl, I apologize. It's now looking a little better. Yeah. What do you have to do to this to make it into that? Black is here, blue is here. Blue doesn't change at all. What's got to happen with the black? The O minus. Needs an H. Where's it going to get the H from? There's no HCl this time. Ah! Ethanol. That's correct. HOET is the solvent and proton source. And that's the reaction we learned in chapter 16 when we combined it with 15, like organolithiums with ketones and aldehydes, right? That's not a new reaction at all. The conjugate addition will make sense if you realize that the word conjugate is synonymous with resonance. There's going to be resonance in the mechanism that you didn't talk about with the 1,2 addition. Now, I will put these back on here. You don't need this on your exam ever, but here's the resonance form. Well, oh boy. Here's the resonance form for that species there, isn't it? If I resonated the pi this way and there, hey, that's a cation there, isn't it? It's another position that is of interest to the anion here. But it's because these diminish, it's not very positive at all. I hope you can see that. It's a very tiny positive. We'll talk about that in a second. The electrons are hitting atom position number 1. And did we do that in hot pink? Yeah, we did. 1, 2. They're going to flow all the way up to the 4 position. Watch. Hey, there's your 1, 4. So you just label the thing being attacked as 1 and just count until the electrons stop moving. And it's 1, 4. And you'll get something that looks a little like the product below. And we'll do the carbonyl OET, carbonyl OET. New bond is here. dimethyl. It's here. And we're going up, double bond here. O minus. I got to point out that's called an enolate. It's the conjugate base of an enol. Does that make sense? And it resonates. So that's why it's ending with 8. So it's acid base again. To get from there to here, using ethanol again. But please don't put the H on the oxygen. That's not the product. Where's the H end up? Hint. There it is. That position had only one H before. There's a double bond there. I want to be very clear on that. There's one H up there. Now there's 2. So green goes there. So mechanism says resonate and protonate. And you're done. Okay. Good stuff. And then part B is a good question. We'll talk about it after you get that. Which product is the thermodynamic product? That's another way to say the most stable product. Okay, thermodynamic, great word. Heat, right? Thermodynamic, changing. What's the opposite of dynamic? Stays the same, but there's a nice engineering word for this. Static. She went to another very valuable word. Very good. So she used the word kinetic. Kinetic is the opposite of thermodynamic. Thermodynamic is constantly in motion, dynamic, and static means stays same. So the opposite. Well, just remember, potential and kinetic are intimately linked. You can't talk about one without the other. So in a thermodynamic reaction, you always are trying to make the more stable product, which means lowest potential energy, right? So we're always talking about potential energy when we're talking thermodynamics. And that's when you talk about stability of molecules. Kinetic, we'll talk about shortly. That's when there's something that's just so compelling for something to happen that that's the only thing that happens. Like if I used an organolithium up here, it's going to attack the carbonyl right here, like this one, 99.9% of the time. And that's true here too. This anion prefers the more positive carbon 99.9% of the time. The difference here is when this attacks, the reaction's over. But when this attacks, the reaction is not over. What am I trying to say with these edited arrows? What am I trying to say with these edited arrows? This will not have that same arrow. This is a new, it's going to react with an E, and it's going to be done. What's the difference between these arrows and this arrow? Equilibrium up here. No equilibrium here. Most important question of the day. Why would this attack or this attack both be equilibria? And this one, once it happens, you're done. There's no coming back. It's very unstable. It is the worst leaving group you can possibly think of. For it to come back, it has to leave, right? What's the opposite of a nucleophile attacking? Something leaving. For this to leave, it has to be relatively stable. It is not when it's an organolithium, okay? When it's the conjugate base of an acid with a pKa of 10, like this thing, it's stable by itself, okay? When you're the conjugate base of an acid with a pKa of 50, you are not stable in any way, shape, or form, okay? So, because you've allowed equilibrium to happen here, you go all the way to the end, because this is also equilibrium, and this is also equilibrium, and I don't know how to get that one to go backwards, but that's pretty good. All you need to look at now are these two products. If equilibrium's involved, then stability is the only factor. In fact, I'm going to unhighlight that. You only need to look over here and compare to only looking over here, because the other part's a constant. What is the least stable part of each highlighted pink area? The least stable bond in both highlighted areas is which bond? Pi. Which pi bond is stronger? One between a C and an O, or one between a C and a C? Yes, any bond to O is stronger than any bond to C. Okay? O is more electronegative. It makes stronger bonds. So now you've identified that this is the most stable product. I don't know. Most stable conjugate addition product is more stable because C-double-O pi stronger than, and you're comparing it to C-double-C pi. There's a C-double-C pi, right? There's a C-double-O pi. I like C-double-O. So finishing our discussion, it's going to be a verbal answer for C, okay? In an equilibrium reaction, or in two equilibrium reactions, the equilibrium that forms the more stable product will always predominate. Maybe I should write it down. Seems pretty righteous, right? I always like checking out the speech recognition on this thing. I always get a laugh out of it. In two equilibrium reactions, I didn't hit the speaker yet. Good. In two equilibrium reactions, that's hilarious. It says in illegal entry in reaction. And that's clearly what I said. No. I gotta stop. All right. Okay, that's all on video too. What a waste of your time. I apologize. In two competing equilibrium processes. Oh, fancy word. The one that forms the more stable molecule predominates. There's your answer to C. So in this case, the 1,4 addition wins out over the 1,2. So you get like more than 90% this product and only about 10. Even though the nucleophile attacks this position 99.9% of the time. It's equilibrium, right? So even though out of 1,000 hits, only one of them goes this way. But equilibrium means they're all ending up here. Because this thing's going backwards and saying, I'm not that happy. I'm not that happy, I'm going back. Oh, when it goes here, I'm a little happier. Okay? And then it's here. I don't know if that's a good explanation of the happy stuff, but go with that sentence and you got the meaning.